Hi, thanks for joining us for this, I think the third video in this chapter about SN2 reactions, and we're continuing to examine different factors that influence this reaction, right? This is something we covered earlier, but there's the electrophilic substrate, the nucleophile that attacks, remember sodium is not part of the picture, and then all of that happens in a solvent. You don't want to forget that this is not something that just happens on paper, but it's something that happens in real life. And so you want to think about all these factors. We considered the nucleophiles last time. Today we want to think about the solvent. That's the majority stuff that all these reactions happen in. Remember, the minority is the solute, majority is the solvent, which usually is a liquid of some sort. So let's think about the solvent effects. And at the best solvents for SN2 reactions, just to give you sort of the end conclusion, are the polar, what we call polar aperiodic solvents. FTW is kind of a millennial thing. If you don't know what that means, you can look it up. What, of course, hopefully you could tell what we mean by the word polar, but what do we mean by aperiodic? That A means like not, right? So not protic solvents, meaning that there's no protons that are easily taken off of the solvent. Okay, so and the reason, and then we'll look at examples, and then it'll probably be more clear. And the reason why it has to be polar aperiodic solvents that are good for SN2 is that the solvent has to be polar enough, solvent molecule have to be polar enough to dissolve the polar nucleophiles. If you think about all the good nucleophiles, right, all of these are actually really polar molecules, and so for that reason the solvent has to be sufficiently polar to dissolve those polar nucleophiles. And protic solvents, if you have a protic solvent, that would lower nucleophilicity for the reasons we'll discuss in a second. So, to explain what a aprotic solvent is, we should probably first explain what a protic solvent is. That means you have a hydrogen on a heteroatom. Often examples are like water is a good example of a protic solvent because you have hydrogen on oxygen, right? Or alcohol. Etc. So it's really anything that has a potentially acidic proton. That's a protic solvent, okay? But the good definition is hydrogen on an heteroatom. So why is that? Like, let's say here's a nucleophile, bromide, okay? It's kind of a decent but not a great nucleophile. If you dissolve that in a protic solvent, one nice thing about protic solvents are that they're polar usually, so you could dissolve the nucleophile. So in that sense, they're good. But here's what happens at the atomic level if you dissolve nucleophile in a protic solvent. Remember the polarity in all these bonds, right? Because of that, right, like oxygen would be partially negative, proton would be partially positive. And you might think I'm going to talk about hydrogen bonding, and it's technically not considered a hydrogen bonding, but it's basically the same thing. So partial positive, partial negative, partial positive, partial negative, partial positive, partial negative charges on all these atoms. And what happens is, right, because the nucleophile is by definition electron rich, it's negatively charged often, there's gonna be sort of a partial hydrogen bonding like interaction like this between the negative charge of the nucleophile and the partially positive protons. What that does is the electron density because all these protons are positively charged, partially positively charged, the electron density of the nucleophile is sort of sucked off by solvation. And what we mean by solvation, that's the phenomenon that happens when something is solvated or dissolved into a solvent and the solvent molecules interacting with the thing that it dissolved. Right? That's solvation. This interaction with the solvent molecules. And the end result, of course, is that the nuclear philicity decreases because if you think about it, that means the electron density of the nucleophile goes down, and without electrons you can't act as a nucleophile. Hope that makes sense. And then I might add this has more pronounced effect on the smaller nucleophiles. For example, like fluoride is not a good nucleophile to begin with, but it gets even worse in a product solvent, and whereas iodide doesn't suffer as much. Okay. So that's kind of what that means. So as opposed to, so that's what happens in a protic solvent. So what is an aprotic solvent? Maybe we should give you some examples first. So I'll give you all the acronyms because that's probably how you see them as first. So DMSO looks like this. All right. And DMF looks like this. Okay, and then THF and acetonitrile, which is often abbreviated like this, but that stands for acetonitrile. These are sort of the go-to solvents for chemists when you want to do SN2 reactions. And sort of one other honorable mention is acetone. It's not a very inert, so it's not great, but it works on a lot of things. Okay, and maybe I'll write out the name dimethyl sulfoxide is what DMSO stands for, and DMF stands for dimethylformamide. And THF stands for tetrahydrofuran, but in order to make sense of that, you should know that this compound is furan, so THF is tetrahydrofuran. And it's because if you add 4 hydrogens to furan, you get THF. Okay, and acetonitrile, of course, is acetonitrile. And these are not protic, and you might say, well, how come they're not protic? Because there's protons or hydrogens, but these are not at all acidic type of protons, and they're not on heteroatoms, and that's part of the reason why they're not acidic at all, or partially positive. They're not strongly partially positive. There is polarity in here, like oxygen's much more electronegative than sulfur, so there's that polarity. Again, there's that polarity here, there's some polarity here, there's some polarity here, and so forth, right? So these are polar molecules, but they're not products, so they're aprotic polar solvents. Okay, so these, what we're saying is these are great for SN2 reactions. It's partly because they dissolve nucleophiles well, because they're polar, and they don't interfere by hydrogen bonding like product solvents. And it's technically not hydrogen bonding what we showed, but I think you know what I mean. And another thing that these guys do is they can solvate cations, which are usually the counterions to the nucleophiles. And what we mean by that is because these guys are electron rich and even partially positively charged, right, they can interact with the cation, which is usually the counterion to the anionic nucleophiles, and segregate those away. And why is that good? Well, when nucleophile, like say sodium bromide, is used, bromide could bunch up with the sodium counterion partners because they're opposite charges, they would attract each other, and if that happens, right, like the nucleophilicity goes down because again this is positively charged, and they would take away this electron density from the nucleophile. But if they're if the cation solvated away and not available to interact with your nucleophiles, then the nucleophilicity goes up. Okay, so yeah, so hope that makes sense. And one other thing I would say is in polar aprotic solvents, fluoride experiences nucleophilicity much more than, say, iodide. Iodide's nucleophilicity goes up too, but the fluoride goes up more. That doesn't mean fluoride is going to be a better nucleophile than iodide. That's not what we mean, but something like fluoride gets to be redeemed more, so to speak, because remember, the hydrogen bonding activity impacts the smaller nucleophiles much more than bigger nucleophiles. And because of the solvation effect, you can actually increase the nucleophilicity of salts like say sodium fluoride much better if you use what's called cation scavengers. And these are really interesting macromolecules that whose size are just so designed to interact with a particular cations like sodium. So this particular compound called crown ether interacts with sodium, and the inner size is just right to interact with sodium, so it tightly binds to it. This is called 15 crown 5. These are called crown ethers. And so what happens if you try to dissolve, like say, sodium halide, which might not typically dissolve in a particular solvent, if you add in this crown ether a little bit, then it dissociates, and the nucleophile becomes available, and then nucleophilicity goes up because it's a lonely anion, which means nucleophilicity goes up. It's nuke. Okay. And this is called 15 crown 5 because if you're pretty sharp, you might have figured this out. Perhaps there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 atoms in the ring with 5 oxygens. So hence it's called 15 crown ether. 15 crown 6. And let's see. See if you can name this. This has 18 atoms in the ring. It's a crown ether. And 6 oxygens. So this is 18 crown 6. And this is perfect for potassium. Okay. Potassium is a bigger ion. Okay, so this interacts just perfectly with potassium, so it tightly binds to potassium. So in an organic solvent, right, like these crown ethers really help because cations and anions tend to bunch up together to lower the nucleophilicity. So some nucleophiles that are not gonna do SN2 can do SN2 if you actually add crown ethers. We'll look at some examples like that in class, but thank you.